Good evening. At the outset, I would like to thank Dr. Ramarao, the organizers of this science festival, for having invited me to give this lecture this evening. I consider this as a great honor and privilege to be lecturing in this science festival. When Dr. Ramarao approached me, I was doing something, I think he called me by phone. There were 3 students in front of me. I said, okay, ಮಾಡೋಣ ಅಂತ ಇಟ್ಬಿಟ್ಟೆ. ಆಮೇಲೆ ಅವ್ರು ಇನ್ನೊಂದು ದಿವಸ ಫೋನ್ ಮಾಡಿದ್ರು, I was about to go for a lecture. ಅವ್ರು ಟೈಟಲ್ ಕಳಿಸ್ಬಿಡ್ತೀರಾ ಅಂದ್ರು. So immediately I SMS the title. Then I went home and I realized what I have stuck my neck into. Okay. And it's a very difficult task, even to lecture formally mathematics to mathematics students. And when you have to lecture to a general audience, students with where we should assume minimal background of mathematics, I think it is an extremely difficult task. And add to that I have unfortunately or fortunately chosen the topic as Ramanujan's mathematics. That makes it even more difficult because there are very few people who can authoritatively speak on Ramanujan's work. So I contemplated for a while, how should I approach this whole process of talking to a general audience about Ramanujan? The first thing that came to my mind was something that is believed about Hilbert, who is one of the greatest mathematicians of the 20th century and the second half of the 19th century. Probably the man who set the agenda for the 20th century mathematics, a German mathematician. He seemed to have said that you never have understood a piece of mathematics unless you can explain it to Mr. T.C. Mitz. And who is this T.C. Mitz? T stands for the, C for common, M for man, I for in, T for the, S for street. The common man in the street. Now, I immediately abandoned his advice for 2 reasons. One, I have no claims that I have understood any piece of Ramanujan's mathematics, leave alone the volume of mathematics that he has done. And secondly, the audience here is not just common. They are science enthusiasts, maths enthusiasts to be here on a working day evening to listen to a lecture in mathematics. They are certainly uncommon man, not in the street, here in the hall. Okay. So therefore, I abandoned his idea. So what do I do next? Then came to my mind an editorial I read in a journal about 30, 40 years back by Ian Stewart. He was commenting about how any mathematics lecture within a few minutes deviates in such a technical way that probably 1 or 2 persons understand what is going on, and many a time probably only the speaker understands what's going on. And therefore, he was saying, why is this happening? It is because mathematicians have this habit of getting into too much technical very soon. So his advice was, damn the details, keep the spirit of the exercise. So I will partially follow his advice, half of it I will definitely damn the details, for the simple reason I don't know the details, and therefore it is fine to follow his advice and damn it. But I do not know whether I am capable of keeping the spirit of Ramanujan's work. It is extremely difficult, but I will try my best to bring some of the spirits. So now I got half advice, damn the details. So where do I go? Then finally came to my rescue another editorial which I had read about 40 years back in another math journal. It was by John Ewing, who also made a remark like this. I was sitting in the hall just now in the office. Professor Ramakrishna was very nicely explaining today's exciting thing, the so-called Higgs boson, particle and all that. And there was no problem. He was very fluently and very simply explaining, sitting at the chair and then we were listening at the table. And this is precisely the idea that John Ewing was trying to bring in his article, in his editorial. He said, whenever you go to a physicist or a biologist or a chemist and tell him, look, I am not a specialist, I don't know much physics, I don't know much chemistry, I don't know much biology. Can you tell me what's happening in biology or physics or maths? It's very likely that this professor would say, okay, it's something like this. And then start explaining very nicely in the common man's language. So Ewing said, why can't the mathematician learn to say it is something like this? Okay, so my talk today will be fully following Ewing's advice, it is something like this, and half following Stewart's advice, damn the details, and completely ignoring Hilbert's advice that nobody here is common and I am not understood any piece of mathematics of Ramanujan so well to claim that I can explain it to the common man. Okay, so with that, this is what Ewing says. You must learn how to say it is something like this. So this is my first experiment to see whether I know how to say it is something like this. Okay. I do not want to get, can you hear like this? I love to walk and talk, okay? Walk the talk, as they say. And also, mathematicians love to touch their expressions. Okay, that's something special about it. No, it's here. I know that. I deliberately want to avoid it sometimes. Okay. Anyway, I do not want to get into talking about Ramanujan's life and biography. Lot has been written about it. Many people have written again and again and again about Ramanujan's life. Very rarely one talks about his mathematics. And most of the time what happens is people, I have myself done this, they'll say, first half I will talk about Ramanujan's life, and second half I will talk about his mathematics. Then go on talking about his life, and at the end said, I am running out of time, so I will talk to you about his mathematics some other time. So I do not want to get, today I am going to experiment, stick my neck deep into it, and try to explain some of Ramanujan's mathematics. Okay, some samples. Okay. So one of the most outstanding contributions of Ramanujan is in the area of partitions. So therefore, before I explain what is Ramanujan's work on partition, I must tell what is partition. Of course, we partition with a wall, 2 rooms, something like that only we are going to do. So it's something like that, okay? So what are partitions? Okay. So suppose I have 3 1-rupee coins. Okay? 3 1-rupee coins, and I want to distribute them. In how many ways can I distribute? So this, I have stated the problem in a loose language. Mathematical problems have to be stated very precisely. As you start doing it, suppose I give a puzzle to some kid and said, can I put this piece here? Can I put that piece there? They start asking doubts whether these rules of the game allow this or not. So we have to make the rules of the game clear as we go along. But the first level statement of the problem is, say something like this, I have 3 1-rupee coins, I want to distribute it, in how many ways can I do it? So, therefore, now next level is, I am going to clarify what I mean by this distribution problem. The first thing is, all the coins are alike. Okay? Well, you cannot distinguish them. All are 1-rupee coin, all were minted in 1979 or 1980, same year. So one coin looks exactly the same as the other coin. So all the coins look alike. You can't break the coin. Okay, it has to be distributed as a whole 1 rupee. You don't go and convert 1 rupee into 100 1 paisas and say I will distribute it to 100 people. No, not that. And then I can give all of them to the same person, the person to whom I give it is irrelevant. Whether I give 1 rupee to him or and 2 rupees to him, or 2 rupees to him and 1 rupee to him, it is the same. I have given one person 2 rupees and one person 1 rupee. That's all it means. The order, the person is irrelevant and the order in which I give is irrelevant. Suppose I take 2 rupees and I give him 1 rupee, or I give him 2 rupees and I keep 1 rupee, I reverse the order, but it is irrelevant. There is a 2 rupee partition and 1 rupee partition. So the order is irrelevant, person is irrelevant, coin cannot be divided and coins are all alike. So these are the rules of the game. Now in how many ways I can make these distributions? Let's look at this simple problem. First of all, I can give all the 3 coins to one person. All 3 1 rupee coins to just go and give it to him. That's one way. Everything is given to one person. Or I give 2 to one person and 1 to the second person. Or I give 1 to 3 different individuals. So therefore there are 3 ways of distributing 3 pieces of 1 rupee coin. Let me again explain it to you. These are the 3 coins. All of them go to the same person, or I write it as 3. It's one cover contains all the 3 coins. Then I will put 2 and put a partition. And then put the other one in a different color. Okay, so that's why it's called partition. So I'll write it as a 2 and a 1. Or I can put 1 and then a partition, 1, another partition and 1. So this I will write as 1 plus 1 plus 1. So there are 3 distinguished ways of distributing 3 1 rupee coins. So we will write this as P of 3 is equal to 3. That P means partitioning. The number of ways of partitioning 3 is 3. There are 3 ways of partitioning the 3 coins. Okay. I hope that's fairly clear. Okay. One of my friends, I have this very bad habit of digressing quite often. I have a very good friend, philosopher, guide, mentor, everything, very senior to me. He used to say that when you give a lecture, at least the first 10 minutes, everybody should understand you. I hope I have satisfied this criteria. Okay, that's why I chose this. So now, I will denote by P of n the number of ways I can define if I have distribute if I have n coins instead of 3. We saw the example as 3. Now I may have 4 or 5 or 6 and in general n. So we want to look at the number of ways I can partition n. Okay. Let us look at 2. That's the easiest case, even easier than 3. I can give both the coins to one person or split it as 1 and 1. So I have P of 2 as 2. The number of ways I can partition 2 is 2. What is P of 1? There is only one way of distributing it. So I give it to one person and there the story ends. So P of 1 is 1. So let us consolidate our knowledge so far. P of 1 is 1. P of 2 is 2. P of 3 we found as 3. Now does anybody want to make an educated guess for P of 4? Anybody from the audience? Yes? 3? Louder. 3. 6. So your guess is 6. Now I said educated guess. Therefore there must be a reason for that. Why do you guess it as 6? P of 4 can be done in 6. Okay, I will not go into without calculating. First of all, I want to see a pattern. Do you see any pattern? Yes, people are a little bit shy in the beginning. We are never used to asking questions in the class and expecting an answer from a student and discussing that answer of the student. But unfortunately we don't do it. That's where, anyway. See, for example, in one of the schools, when I asked this question, one of the students said P4 equal to 4. I asked him why. Sir, P of 1 is 1, P of 2 is 2, P of 3 is 3, so therefore P of 4 must be 4. That is the pattern he saw. Then there was another student in another school, he said it is 5. Can you guess what his reason would have been? So now you see I want to touch. You see 2, 3, what are their prime numbers? So he said the next prime number is 5. Therefore, sir, likely it is 5. Then another student said, all these answers I got from students, okay. Another student said, sir, he is right 5, but his reasoning is wrong. I asked him, then why do you think it is 5? He said, sir, 1 plus 2 is 3, so 1 must be 2 plus 3 equal to 5. You see, this is what is important. The same thing, different minds see it in different ways. Each one thinks he is right. Okay, that is why so much money is spent to test whether a boson exists or not. Nobody believes, okay. Anyway, so there are different minds. Maybe he's bluffing, it doesn't exist and things like that. Okay. Anyway, so therefore now there are now many guesses. P4 must be equal to 5. One fellow has one reason as it is the sequence of the prime numbers. Another person has another reason that it 1 plus 2, 2 plus 3, so next one must be 2 plus 3 equal to 5. My friend here says, I calculated, actually wrote down the partitions and counted, it came to 6. So I got another answer, so I should write. So now let us go and see whether, do the boson experiment and see whether that 5 is right or wrong. Well, 4, I can give all the 4 to one person. Then I can give a 3 and a 1. Then I can give a 2 and a 2. Then I can give a 2, 1, 1. Then I can give 1, 1, 1. How many I got? 5, not 6. Okay. So these two school kids were very delighted when I showed them that the actual answer is 5. And both of them started fighting that my reasoning is right. Okay. So therefore I said, okay, let us see who is seeing patterns better. So let us now consolidate what we have got. P of 1 is 1, P of 2 is 2, P of 3 is 3, P of 4 is 5. So suppose I had 5 points. The student who saw the pattern of the 5 numbers will say the 7. But the other student will say 1 plus 2 is 3, plus 3 is 5, so it will be plus 5 equal to 8. So these students, now I said, let us put you both to a test. And then one fellow said 5, the 7 and the 8. So let us now calculate 5. All 5, a 4 and a 1, a 3 and a 2, a 3 and a 1 and a 1, 2 to 1, 2, 1, 1, 1 and 1, 1, 1. How many have got? 7. So the prime number boy jumped in his seat. I am right. Okay. Now these days they do this. This is a great sign of victory. And the other boy started crying. So I was wrong. Okay, I said, don't worry, I will pacify you shortly. So now, what have we got? Consolidate. P1 is 1, P2 is 2, P3 is 3, P4 is 5, P5 is 7. So what is your guess for P6? And the one sat there crying because my prime number friend, the boy immediately jumped and said the next prime. What is the next prime? 11. Okay, so let us check whether it is 11. I will write all the partitions of 6. So that's all. 6, 5 and 1, 4 and 2, 4, 1, 1, 3, 3, 3, etc. Stop. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And that boy hit the ceiling. Jumped. Said, sir, See sir, I have done correctly. Said wonderful, so we have got all this. So what is your next guess for T7? Yeah? Should be 13, the next prime, right? So, let us write. I listed all these. So the other boy also started crying. My answer is wrong. Okay. Now as it goes on, almost all the mathematicians started crying. So they didn't know what was happening. So now, we have lost all the pattern. This simply doesn't, seems to be a pattern that for some time there appeared a pattern and then completely it disappeared and the thing gets worse. The numbers become higher and higher. I listed some of them. Now here is the next example. You have a look at it. Okay? 92, not that, followed by all this. 9-2 followed by all this, not just followed by all this, not just followed by all this, and followed by all this, and followed by all this. There are 127 digits in the number of ways we can partition 14,001. So now we have a real difficulty. Can we get a formula for Pn? You see any pattern? Everything is broken down. Okay. These days we see a lot of pattern recognition and other things. When the problem was there, not the whole of European mathematics completely was dumbstruck and they didn't know any formula. Then comes Ramanujan. Ramanujan just pulled a rabbit out of the hat and says, N is that. Okay? That's amazing. I mean, where, to this day, nobody knows how we came up with this formula. Okay, so now, I won't even comment about the formula, all the terms. See, if you are a bit of mathematics, the problem is a discrete problem, involves integers, but this involves differentiation, which involves continuum process. How are these things connected? How did he go to this? But that's okay, that's not a big problem. Actually, these things happen. But then, one significant thing that I want to point out is the Ramanujan did not put equal. It's a little bit tricky there. It's like this. What does that mean? That means it is approximately equal to that. Not exactly that, but approximately equal to that. Okay? Okay. So therefore, there must be an error. If you calculate from his formula, and his formula is approximate, and therefore there must be an error. What is the error? What is the exact value? And what was calculated by Ramanujan's formula, the difference is the error. So Ramanujan asked the RD, what is the error? Oh, I know the error, he says. Then he says, the error is approximately equal to some alphabet, T to N, okay? So the error is approximately equal to something. Then he says, okay, then what is the error in the error? It is approximately equal to this. Approximately equal to this. And goes on and on and on, and finally it is a infinite series. Then it is equal. P1n, P2n, P3n, P4n, P5n, everything goes on right. And says, Pn is that. But then Hardy had a problem. He said, okay, let me substitute n equal to 200 and calculate what you get. But what happened was all these added up to infinity. That is what mathematicians say. Here is diverges. Okay. Everything, that means the sum, if you add the first term, second term, third term, it goes on increasing without any bound. Unboundedly it goes on increasing. Then Hardy asks, how can I divide 200 coins into an infinite number of ways? It is impossible, your formula is wrong. Then Ramanujan says, who asked to sum all? Who don't sum all the terms? I will tell you. Okay, I will skip this. Okay, here. He said, if you want P of 2000, you take square root of 2000, that number is between 44 and 45, the closest integer below it is 44, you take 44 terms in the series I wrote. Don't worry about other terms. Take the first 44 terms and sum. Then again Adi goes and sums all the calculators, not the olden day calculators. Then he got an answer which was something like some big number and an additional 3 by 4, a fraction. Then Adi came back, comes back. This is how it must have happened. And asked Ramanujan, how do you divide 200 coins in a fractional way? The number of ways I divide must be a whole number. So he said, don't worry, ignore that fraction. Take only that whole number. And lo and behold, he was right. It worked. So what was Ramanujan's formula? Whatever he wrote, depending on n, how to choose the number of terms, and once you choose the number of terms, you calculate what you get, take only the integral part of it, and that will be Pn. And it worked. See, in his days, in Ramanujan's days, first they had only a table which was the table part of the table for the values of Pn by one British Major Mathemagics. He had calculated up to 200. So they checked up to 200. In fact, Ramanujan, in his paper that he published in the Cambridge Philosophical Society, he writes after 153, after checking for 103, he said, it is totally unnecessary for me to anymore check for P n equal to 200. It is going to work. Okay. That was the confidence this man had. Okay. Now, that formula is called Hardy-Ramanujan formula. Where did Hardy come in? Because he was running back and forth, doing the calculation. No, Hardy had a terrific contribution to it. Namely, Ramanujan gave the formula and he never bothered about giving proof. He is working, why do you worry? I know it works. He didn't bother about giving proof. So Hardy sat with Ramanujan and worked out proof, and that is called the circle method. The circle method, because of the development of the circle method, it is called the Hardy-Ramanujan formula. Okay. So that was his first fundamental contribution in number theory. The first and part of the work, partition, that is first simple illustration. And then continue with partition for some more time. Okay. Now, this Ramanujan takes this table that McMahon has prepared, has one and starts saying this should happen, that should happen, that everything. Now let us see what are the things that he says. Okay. So now I am going to get into, so first I will show you a table. I will explain this table to you. This column says n and the corresponding value of similarly. Continue this table, n, I listed up to 68 because I did not put all the 200 in one slide and I didn't want to split them into many slides. It just gives you a feel for the values of. Now, do you see any pattern? Mortal eyes like ours cannot. And they did not. So what I will do is, I will do Ramanujan's magic and focus on values in the table. Not all of them. Okay? What am I going to do? I am going to look at values 4, 9, 14, 19, n. These values are n only. What do you see in these values? Yes? Okay, all are a multiple of 5 plus 4. Okay, they are 5k plus 4. First one is 5 times 0 plus 4. Second one is 5 times 1 plus 4. 5 times 2 plus 4. 5 times 3 plus 4. So, what I have focused in that huge mess of the table, Ramanujan's eyes could focus on these values. Okay? And now what I am going to do is I am going to fill up the table. What are the corresponding values of Pn? Okay, incidentally the number I have chosen is of the form 5k plus 4 is mathematically written as 4 mod 5. Means divided by 4 you get remainder 4. That is a technical way of writing that those numbers 4, 9, 14, etc. Now, I am going to fill up the table. For those values, I have filled up the values of Pn. What do you see? Anything that you observe? Somebody said multiples of 5. See, wonderful. I isolated that, you saw the pattern, and that you was able to see. See, they end up with 0 or 5. They multiples of 5. That's not great. Now what Ramanujan said was, you calculate for any n, this will always happen. For any n, which is of the form 5k plus 4, which is not even in this table, I don't care, it has to happen. So that was the first major, what is a conjecture. He said, this should happen. Okay? Alright. Whenever you take a number of this form, 4 plus a multiple of 5, the Pn value, we should leave remainder 0 when divided by 5. Technically that means Pn is consequent to 0 mod 5. It will not leave any other remainder, it will be completely divisible by 5. Now he didn't prove it. He just said it is true. I know. That's all. I know and that's final. Okay? Now, that is one focus. The values 4, 9, 14, 19, etc. Now another focus. Okay? So all this focus went in Ramanujan's mind at that book. And he saw farther beyond the table, even those values which did not exist in the table. Now what are the values I have taken? 7, 5, 12, 19. Now they are all multiples of 7 plus 5. 7k plus 5. 7 times 0 plus 5, 7 times 1 plus 5, 7 times 2 plus 5, 7 times 7 times 3 plus 5, 7 times 4 plus 5, etc. So these are numbers of the form 7 times k plus 5. Okay? And then let me now fill up the table. What are all the values? Now do you see a pattern? Do you or do you not? They are all divisible by 7. Okay, and Ramanujan said this will happen. However far you go to the table, this should happen. So that was Ramanujan's second conjecture. That if you take a number of the form 7k plus 5, that is when it is divided by 7 it leaves remainder 5, the Pn will always be divisible by 7. There is another third conjecture. Again, he looks at his eyes focus on different things. What are they? Are all multiples of 11 plus 6. So, 6 plus 11, 6 plus 2 times 11, 6 plus 3 times 11 and so on. Okay, they are all of this form. Then let's again fill up the tables. Now what do you see? They are all divisible by 11. All the values are divisible by 11 and Ramanujan, that is his third conjecture. Okay? It is all of them are true, okay? That is his third. We take a number of the form 6 which leaves remainder 6 when divided by 11, the Pn value will always be a multiple of 7. Now, a small few snippets I will make before I make a major statement. Let us look at these three congruences. These are all called congruences. We saw three cases. The first case we looked at numbers of the form 5k plus 4. Second case we saw numbers of the form 7k plus 5. Then we saw numbers of the form 11k plus 6. So, these were the three cases that we saw. Now, Ramanujan makes a very wonderful observation. In each one of these things, there are important things. One, prime number 5, and then the remainder 4. These are the two important things. Here there is a prime number 7 and the remainder 5. Here there is a prime number 11 and the remainder is 6. Now he looks at this remainder. I think how we even ever thought to look at them that way is amazing. He says, take 4 times this remainder. What do you get? 96. Divide it by 5, you will get 1. Take 24 times this remainder. What will you get? 120. When you divide it by 7, what will you get remainder? 1. You take 24 times this remainder, 144. Divide it by this prime. What remainder do you get? 1. That is an amazing observation. Okay. All these are of this type. Now comes the trump card. And there, this is all probably, maybe, if I was born about 60, 70 years ago, before then what I was born 60, 70 years ago, no question about it. But if I had born 60, 70 years before when I was born, and if Ramanujan had not been born, probably by fluke I would have found this. Okay? Anybody, but what Ramanujan goes on to make is the real trump card. Okay? Now what Ramanujan says is, can I think of any other prime number other than 5, 7, 11 and any other remainder instead of 4, 5 such that when we start with the on taking multiples of that prime, look at the Pn values, it was T. When I all 4, 9, etc., it was divisible by 5. When I took 5, 12, etc., Pn were divisible by 7. When I took 6, 17, etc., Pn were divisible by 11. From that, if I take a prime T, K, R, that will be right? This was the question that came to his mind. These are the three. And he said, no more. You can stand, do whatever you want. You will not find anything more than this. These are the only three possible such patterns you will find. There does not exist any more such pattern. Okay, and this is something which I think, even if I had born with 100 times more brain than what I have, but 100 times greater teachers than I have, even if I am 100 times more intelligent person than what I am. And even if Ramanujan himself had taught me, probably I would never have seen it. This is the most profound statement he made. Why profound? I will tell you. This is what his statement is. It appears that there are no more simple such things. Very calmly he says that. I see it, it appears. It has appeared in presence of his eyes. There is no more such simple congruence. Now, the problem is when somebody says like that, nobody believes. Where is the proof? Where is the proof? That I don't care, I see, if you don't see, this is not my problem. Okay. So then, okay. So, we are looking for prime numbers of this form and divide p, the p values will give 0. And 72 years after Ramanujan's death, this fellow proved that if at all there is anything I don't know, this R must be like Ramanujan's. 24 times that R, we remainder 1 when divided by 2. I don't know whether it exists, but if there exists, corresponding R must be such that what in my 24 times R minus 1 must be. Okay. Another 11 years later, okay, 2003, that is 8 years after Ramanujan's death, this guy proved, yes, not only that, there have to be 5, 7 and 7, nothing else. So, I was just, when I was talking in this coffee room, I was telling them about one show I saw on BBC TV about Feynman. Richard Feynman once, he was the author of this great standard model in physics which people are talking about. I know nothing about it. Anyway, Feynman was explaining in that program that once he went to CERN, the place where all this boson thing is going on, and the director of the man in charge of that place called one young postgraduate fellow and said, check our visitor from the US around our labs. So this young man wanted to impress, he didn't know it was Feynman, so he took him around CERN, apparently saying, this magnet costs $2 million, this equipment costs $4.5 million, and so on and so forth. Then, very proudly, then Feynman asked this young man, what are you going to do with all this? Then he said, sir, we are going to test whether Feynman's theory is correct or not. Then Feynman said, my young man, you don't believe me, do you? Okay. So probably nobody believed Ramanujan. They always suspected, try to prove, try to prove that he was wrong. Finally came to the conclusion that he was right. Okay. So this is considered, I would say, as one of the great, fantastic things that Ramanujan contributed. Theory of partition. I have only said very simple things about what partition is, what is Ramanujan's formula, how got it, we don't know. The patterns that we saw in these partitions. Okay. Now, I'm brought you in a time. What time I should stop? No. No, when I said you should give me a clear time, not give me a free time. Okay? It is another half an hour. You whatever time you say, because you see, I always advise my students that when you give a lecture, you should have one slide to which you should be able to switch and finish your lecture in 5 minutes. Okay. That trump card slide must be there with you. Okay, so I can finish my lecture anytime within 5 minutes. Okay. Now I am going to look at another important of Ramanujan. I think this is one of the greatest contributions of Ramanujan in mathematics. It is called the tau function. Some of you might have heard about it. And some of you might not have heard about it. I had not heard about it until I was in MSc and not in the classroom, while walking with Professor Venkatachalanga from Central College to Seshadripuram towards his house. I learned some good mathematics in classroom. So I advise that some of you walk with your professors home, but unfortunately these days nobody walks. As soon as they come out of the room, there is a car or a scooter or something like that, everybody flies out. Okay. In our days we used to walk. Okay. We had no choice. Okay. Okay. In one of these papers in 1916, Ramanujan introduced this tau function. Now, about this tau function, this is what Bruce Berg has to say, which was the most important paper in the history of number theory. And it is not a paper on tau function. In fact, I was wondering where from the beginning. Then I found there in the middle of this paper, he introduces that thing and goes on making a few statements about it. So now I'll tell you what is tau function. Okay, so that we understand what's going on. So let me begin at the beginning. Okay? So start with some preliminaries. Everybody knows this formula, right? There's anybody in the audience who doesn't know this formula. If you don't know, keep quiet, okay? Pretend that you know. Probably little bit shaky about this, but most people know about this. Right? Okay. Now, what is generalization of this is what is known as binomial theorem. Instead of 2 or 3, I put a general. What is the expansion? That's what probably you taught at PUC level, the binomial. A plus B is all this. Now, I am going to specialize on this. Use special value for A, special value for B. So I will take A equal to 1, B equal to minus x and write down the binomial theorem. And I even took 24th part. See, this 24 is a very popular Ramanujan. Okay. The 24 r minus 1 was. So I am going to look at 1 minus x to the power of 24. The expansion is like this. What I want you to observe is, whenever you have such a thing, when you expand, there will be a constant term, there will be an x term, there will be an x squared term, and so on and so forth, up some powers are. Now, I will put, instead of x, I will put x squared there, and expand 1 minus x squared to the power of 24. So wherever there was an x, now x squared will appear. So x squared squared becomes x to the power of 4 and so on and so forth. And then I will put x cubed, x to the power of 10 in general. Okay, I will put, in place of x, I will put x power n. I will get, wherever there was an x, I will get xn. Now I multiply all this. When I multiply all this, get a huge expression, still some constant, some x term, some x squared term, some x cubed term and all. I don't like the constant term. I will multiply by an x also. So, when I multiply everything and multiply it by x, the expansion will start with an x term. Okay, so it will have something into x, something into x squared, etc. That thing which comes in front of x to the power of n is called the tau of n. That is Ramanujan's tau function. The tau of n is the coefficient of x to the power of n in that big expansion. Now, why is that big expansion? That has something to do with modular forms and all. We will not get into technical. I will just try to explain what the tau function is. Okay, so this is what the tau function is. Take expansion. If you have the paper, you can expand this. For example, go home and try what is tau 4, tau 5, tau 6. These are simple. You can expand and see what happens. Okay. So, Ramanujan, as usual, first you prepare a table. See, because the moment you see something, you know what's happening. In a sense, people say He is a great pure mathematician. He was an experimentalist also. He would experiment with a few numbers, and that data will tell him what's happening. He had the mind to see, experiment what is happening. So he experimented with a number, and calculated tower. Again he started seeing what is happening. Nothing. Again, I will not go into the fact he saw a lot of congruences before, like as he saw in PM. But I am not going to go into that. But this, he looked at it for a moment, maximum a moment, and he then starts writing. You should receive that paper within about almost half a page. He dismisses of everything. Okay, probably I would have written a 100-page paper if I had a result like that. Okay. Now I will skip the two congruences. Okay, he makes two comments about the tau function, these two properties. I will not go into it, but they were proved quickly within 1 year by model. Ramanujan didn't give the proof, but anyway it was proved by model. But what I am going to do is the next. Another world famous conjecture, for which again I will introduce some notions. Now to explain this notion, probably let me try. Okay. Suppose, okay, forget about this, okay. Now the audience is, probably some young students will respond. Suppose I have ratio, fraction. I have 1 in the numerator and 10 in the denominator. What is the value? 0.1. If I make the denominator a little bigger, 10 square say, what happens? 0.01. Values come down. Make it 10 cube. Value comes down. Right? In fact, who is it? I don't remember now. There is a famous mathematician who said, your true value is a ratio. A man's true value is a ratio. The numerator is what he knows, and the denominator is what he thinks he knows. The larger the denominator, the lower is his value. Okay. Exactly, that is exactly the idea that I am trying to get. The larger the denominator is getting bigger and bigger, the value is going down. So suppose the denominator goes to infinity, then it will go to 0. Okay. So, when we have a ratio of two functions, f of n divided by g of n, if that goes to 0, then the denominator goes to infinity. So what if the numerator also goes to infinity? Now we are playing a tug of war. The numerator wants to go to infinity, but the denominator fellow wants to bring him to 0. Who wins? It depends on what that function f of n in the numerator is, what that function g of n in the denominator is. If g of n is powerful, quote unquote, then you go to 0. If f of n is powerful, it will go to infinity. If there is some kind of a match, it will neither go to infinity nor go to 0, it will be somewhere in the finite range. And this is the idea which Hardy expressed in mathematical terms as the order of magnitude, big O and little o. Okay? The two notations, very important notations. I think Professor Ramanujan was mentioning about order of magnitude. Okay? This is exactly what the order of magnitude is telling us about how much 1 trillion electron volt means. Only a mosquito, that's all, don't worry. That's a great thing I learned today. I will now very happily ask everybody when he talks about 1 trillion electron volt, what is it? In fact, one day somebody asked me, what is 1 TMC of water? And if you go home and find it. Okay, so now I am looking at it. I have a numerator which goes to infinity. I have a denominator which goes to infinity. The denominator wins. It's very powerful. He pulls him to 0. Then I say, the poor fellow, 0 volt. Small O I put. His order is compared to that of G. But suppose Okay, here is an example. Just copy. The other situation is when they are controlled. Okay? When they are controlled, they neither goes to infinity nor goes to zero, somewhere in the finite range, then we say it is big O of Gn. So big O of Gn means denominator wins. Big O of Gn means there is a tie. Okay? That's all. That is what I meant by it is something like this. Okay? That is probably what we meant. When a ratio, the numerator is of little o of the denominator, that means denominator wins the war. If it is big O, it is a tie. Okay? That's exactly what we will have in mind. But you see, something is big O of Gn, the denominator is already matching the numerator. If I add any more power to the denominator, he will. Because already numerator is able to only match the denominator. You give more power to denominator will automatically win. Okay. So therefore, if Fn and Gn are of the same order, then the denominator increase, then the other fellow will go down to zero. Let's not worry about it. So now comes the great formula of Ramanujan. The greatest conjecture of Ramanujan on the tau function. He said, if you calculate the tau value for any prime number, it will be order of e to the power of 11 by 2. If you put more order, then the ratio denominator will pull it out. You put lower order, numerator will win. Exact matching order for tau of p is the 11 by 2 power. I don't know where you got that 11 by 2 power. Again, this is one thing which just pulled out of the hat. It was so much pulled out of the hat, it just baffled all the mathematicians. They didn't know how he got it from. Probably they tried very hard to disprove him, but they did not succeed. Then, okay, I will show you some attempts. For example, R.D. showed whether it is 5.5 or not, it will certainly not more than 8. Okay, good. Somewhere he succeeded. Then Ramanujan himself wrote some things, okay? Then Ramanujan says it cannot be more than I tell you, 8 is too much of a overestimate. It cannot be more than 7. I know it is 11 by 2, but I can prove it is not more than 7. Then again I have to come back. Okay, I will say it is not more than 6. They are coming close to 5.5. Okay? Then another fellow comes and says, and 47. That is, he said, I am better than Hardy. Hardy is 6, but I am less than 6. Then there is this guy who comes and says, it is 35 by 6. Then Hardy again. Okay? But nowhere they are 5.5. They are still struggling. And then comes probably the last successful attempt in 1939 was 29 by 5, which is 5.8. But Ramanujan's guess was 5.5. Then finally, 50 years after his death, 53 years after his death, so that exactly it is 11 by 2. What Ramanujan. Mind you, Peter Berlin was given the Fields Medal for that. But showing that Ramanujan was right. Ramanujan got nothing. Okay, so for showing that Ramanujan was right, Peter Berlin got the Fields Medal. One good thing was, Berlin used very powerful ideas in number theory like L-adic number theory, etc. that were developed much after Ramanujan's death to prove this. So therefore, Ramanujan must have had some other way of looking at it. Or when Berlin gave that acceptance speech for the Fields Medal, he said, I am very happy today because I have proved Ramanujan's conjecture and I am getting the Fields Medal. But I am also very unhappy today because I have messed up Ramanujan's self function. There must be a much easier way of looking at it. This is considered, these two, this work on partition and self function are two of the greatest things which are easily explainable. But there are many more things which I will not seem to. So what I would do now is, probably I will not get into any mathematics for some time. Can somebody help me with this? There is, yeah, I will close it there. There is one more file in this, right? Right, yes. Open. Outside, yeah? Yes, and then I should go to. What I will do is a few general things. What motivates such a person? A person like Ramanujan. What is what do people say about him? Okay, so I will do these comments. Okay. So the first thing is, why? What makes people in science or art and mathematics or any subject for that matter? What is the motivation? Of course, there are a lot of writings. Some people say it is the pursuit of truth. Some people say it is the pursuit of beauty, or the quest of beauty, or whatever it is. And of course, people, at least I remember, I heard a poem in BSc. It was the word on a Grecian urn by John Keats. And beauty is truth and truth. So it doesn't matter. If he is pursuing beauty, he is pursuing truth. If he is pursuing truth, he is pursuing. It's all that. Okay. So therefore, now what is the business of beauty? Now let us see what Raman says. So what Raman says is, by exploring nature and thinking about it, we see the beautiful things in nature better. That's what he really says. So it is, whether you are pursuing the truth, whether it is a boson particle or not, it is not actually the boson particle that's important. It is the structure of matter that you are looking at. It is its idea of what makes things work. It is these questions that are important. Whether if boson is today, it's true that boson is not there, boson doesn't make it work. And the question still remains, what makes it work? Some other will be there. So therefore, that sort of thinking and that sort of questioning is what makes it better. And Hardy puts it very bluntly. The first test is the beauty. And there is no permanent place. This is simply dismisses that there is no room for ugly mathematics in this world. So therefore, the question is, does Ramanujan's mathematics satisfy this dictum of Hardy? Is it beautiful mathematics or is it ugly mathematics? So obviously we are talking 125 years later, therefore there must be a permanent place. There must be ugly mathematics. So I am going to show you a few examples of what people say. Littlewood. I am sure many of you have heard of him as a wonderful mathematician. The beauty and singularity of his refers to Ramanujan, his entire, the beauty, you see, it refers to his beauty again. Then, Richard asking, Ramanujan is like Mozart. Just like Mozart was beautiful music, Ramanujan had this beautiful math. So again, he seems to come out with flying colors. Michelangelo. And good as seen the great sculptures of Michelangelo. I think any time you get a chance to visit Europe, don't miss visiting Italy. You will see beauty, don't miss seeing all the beautiful works of all the great painters and the sculptors. But be careful with your thoughts. We have to be careful. But here is what in fact Watson probably makes the statement obituary he wrote when Ramanujan died. Okay. But here is the last notebook, you must have heard about it. It's as good as finding the 10th symphony of Mozart, or Beethoven, I'm sorry. Then, here is Dyson. As pure mathematics, it is as beautiful as any of the flowers that ripened in Ramanujan's gardens. So absolutely flying colors, Ramanujan comes out as far as the beauty test is concerned. Okay. So he is the what? Miss Universe, not Universe, Mr. Mathematics. Okay. So therefore, what is it? That was it the beauty? Perhaps yes. What? Probably not. Perhaps not. We don't know. Again, it is only a guess. What motivated him? It is only a guess. So it is meaningless to go on looking at how the mind of the genius works. And I was discussing with our former director, late Professor Ram Session, he said, he just did what he was destined to do. That's all. But what did he mean? For him it was something like, he is the messenger of God. Okay? And he gave me this poem, and I'll read this. As in yonder valley, the myrtle spreads his fragrance into space. Through the hands of such as these, God speaks. And from behind their eyes, he smiles upon earth. So, in a sense, didn't see the beautiful creations in mathematics and number theory for a long time. He had to send a messenger in the form of somebody and say, look, you are missing all this, why don't you look at it? Now when I read this, when I was giving a talk on Ramanujan, just immediately after the Ramanujan centenary in 1987, we all know that just on the day after Ramanujan centenary, the then Chief Minister of Tamil Nadu, M.G. Ramachandran, died. Everybody was talking about someone who was educated across the border in Tamil Nadu, I knew a bit of Tamil also, told them, MGR had a very famous slogan. Does anybody know Tamil here? Oh, who knows? Otherwise I should be careful. I could have been careless. Now I should be careful. MGR's statement was, ஏழையின் சிரிப்பில் இறைவனை காண்கிறேன். What it means is, when a poor man was laughing, I see God in him. Now what this says is, I told them, Ramanujan இறைவன் சிரிப்பை காண்கிறேன். That is, in Ramanujan's mathematics, you can see God smiling on us. Okay. That's And finally, to conclude, and the confusion I created to Dr. Ramarao with my title, Mathemagics, okay, I will say, the famous mathematician by name Mark Hartz, he says, who is a genius and who is a magical genius? A genius is one. When I see his work, if I am little bit, I see how he has done, I feel, yeah, maybe if I had been a little bit cleverer, a little bit luckier, maybe I could have also done it. But a magical genius is one. Even after I know what he has done, I just don't know how he did it. And that is why Ramanujan is a magical genius. And that is why I call it the title as a Mathemagics. Thank you very much.